Have you ever marveled at the incredible productivity of chickens like the Isa Brown, capable of laying more than 320 eggs a year, and wondered where that amazing genetic potential comes from? Here's the riddle. If these chickens are so productive, why don't the offspring of a male and female Isa Brown inherit that same super productivity when bred? Conversely, why do the offspring from a cross between purebreds such as a Rhode Island Red rooster and a Rhode Island White hen, which, by the way, are the parents of the original Isa Brown, maintain predictable, high-quality laying rates? The key to this fascinating mystery lies in the dilution of hybrid vigor and the complex dance of genes. Chickens like the Isa Brown are the result of a perfect genetic formula, where the combination of genes from their purebred parents creates a peak in performance. But when these hybrid chickens breed with each other, that formula breaks down, scattering the genetic potential in the next generation. If you're a breeder who enjoys experimenting with crosses, this information is pure gold. Understanding this genetic phenomenon won't just satisfy your curiosity, it'll significantly improve the results of your own breeding projects. In this video, we'll break down everything related to this exciting topic. Stick with me until the end because, in 20 key points, we're going to cover every detail to understand it perfectly. You won't want to miss it. Let's start this amazing video from the very basics to ensure you grasp the information as thoroughly as possible, since it's a somewhat complex topic for those unfamiliar with it, before moving on to the more intricate points. 1. What is a purebred chicken? Purebreds are the foundation of poultry genetics. They refer to populations of birds that, over many generations, have been selected and bred to exhibit very specific and consistent characteristics. Think of a purebred as a well-established, predictable genetic code. If you see an individual of that breed, you can anticipate with high certainty its appearance, size, egg color, and, to a great extent, its behavior. Developing a purebred involves a rigorous selection process. Breeders meticulously choose individuals with desired traits. For example, hens that lay large, white eggs, or roosters with fast growth and good muscle conformation. By breeding only these selected individuals and repeating the process generation after generation, a great deal of genetic uniformity is achieved within the population. This uniformity is key. It means that most genes in a purebred tend to be homozygous, meaning they have two identical copies of the same allele for a particular characteristic. For instance, if a purebred hen lays white eggs, it's highly likely to have two alleles for white color. This ensures that its offspring faithfully inherit those same attributes. In commercial poultry farming, purebreds aren't typically the birds the end producer buys for their operation. Instead, they are the secret and highly valued ingredients that large genetic companies closely guard. They are the base from which high-performance hybrids are built. 2. Homozygous genetics in purebreds. The defining characteristic of purebreds is their homozygous genetics. This means that for most genes determining their distinctive traits, like plumage color, body size, comb shape, or predisposition to lay many eggs, a purebred individual possesses two identical copies of the same allele. This genetic uniformity is the result of decades, or even centuries, of careful selection and selective breeding within the same line. Imagine a gene controlling egg production. In a highly efficient purebred layer, breeders have consistently selected birds with both copies of the most favorable alleles for that trait. This rigorous approach ensures that the offspring of these pure parents will inherit a very similar genetic combination, leading to exceptional predictability in their productive traits. There are no unexpected genetic surprises in the next generation. This homozygosity drastically reduces genetic variability within the breed. While this can make them more susceptible to certain challenges if the environment changes drastically, or if they face new diseases, due to their lower genetic diversity, it's precisely what allows them to be the solid foundation for breeding. Their genetic stability makes them reliable building blocks for more complex breeding programs. In modern poultry production, this homozygous genetics of purebreds is what allows genetic companies to have precise control over outcomes. They know exactly what to expect when crossing two specific pure lines, as the starting genetic material is inherently uniform and predictable. It's why purebreds are valuable genetic assets, closely guarded by the industry. 3. Heritability in purebreds. Heritability is a fundamental concept in genetics that describes the proportion of observed variation in a trait, such as egg size, growth rate, or disease resistance, that is due to genetic differences among individuals, rather than environmental factors. In the case of purebreds, the heritability of their key characteristics is remarkably high and predictable, which makes them invaluable for breeding programs. Thanks to the genetic homozygosity that characterizes purebreds, the traits exhibited by their parents are highly likely to be faithfully transmitted to their offspring. If a purebred hen is known for laying eggs with a deep brown shell color, it's almost certain that her chicks, upon maturing, will also lay eggs with that same characteristic. This consistency is crucial for the stability and recognition of each breed. This high heritability means that when a purebred breeder performs a mating, they have a very clear expectation of the characteristics that will emerge in the next generation. There are no major surprises regarding individual productivity or flock uniformity. Traits like feather color, body shape, temperament, and basic production patterns remain constant from one generation to the next. Therefore, purebreds serve as a reliable genetic recipe book. They allow breeders to isolate and maintain genetic lines with well-defined specific attributes. This predictability is essential for the next step, the strategic creation of hybrids, where these pure lines are crossed in a very deliberate way to exploit their complementary characteristics. 4. Crossing purebreds, also known as pure line crosses. Crossing purebreds or pure lines, such as breeding an improved Rhode Island Red rooster, known as a pure line of this breed, with a genetically improved pure line Rhode Island White hen, is the cornerstone of modern poultry production and the starting point for creating high-performance hybrid chickens. This isn't a random mating, but a highly scientific and strategic process, planned decades in advance by specialized genetic companies. The goal is to combine the genetic strengths of two distinct purebreds or pure lines to obtain superior offspring. To achieve this cross, genetic companies invest millions in the research and development of their own pure lines. These lines are meticulously selected for their complementary characteristics. For example, one pure line might excel in producing a high number of eggs, while another might contribute larger egg size or better resistance to certain diseases. The art lies in identifying the combinations that will maximize offspring performance. The process involves mating males from one purebred line with females from another pure line. The results of this first cross are the F1 hybrid chickens, which are the birds that poultry farmers buy for their commercial operations. This first generation is the pinnacle of efficiency, as it inherits a unique combination of genes that unlocks its maximum genetic potential. The key to success in this cross lies in the genetic distance between the pure lines used. The more genetically distinct the parental breeds are, the greater the manifestation of hybrid vigor in the F1 offspring. This meticulous mating is the secret behind the astonishing productivity of the commercial chickens we see today. 5. Definition of a hybrid chicken. F1. A hybrid chicken, F1, such as the Isa Brown, is the direct and specific product of a cross between two genetically different pure lines, carefully selected for their complementary attributes. These are the birds that dominate commercial poultry farming, from brown or white egg layers to fast-growing broiler chickens. When a producer buys day-old pullets or day-old chicks from a specialized company, they are acquiring precisely these F1 hybrid chickens. The term F1 stands for first filial generation, indicating they are the direct offspring of the first planned mating between the parental pure lines. These birds are not a breed in the traditional sense, as they don't breed true, and their offspring wouldn't maintain the same uniform high-performance characteristics. They are the end result of a genetic improvement program. What distinguishes an F1 hybrid chicken is its extraordinary efficiency and productivity. They have been genetically engineered to excel in a specific trait, such as massive egg production with excellent feed conversion, or extremely rapid growth with great efficiency and resource utilization. They are true production machines, optimized for commercial performance. It's crucial to understand that these birds are the finished product of the crossing process. They are not intended to be breeders for the next generation on a commercial farm. Their complex and specific genetics grant them their high performance, but that same complexity makes their reproduction unpredictable and undesirable if maintaining productivity is the goal. 6. Hybrid genetic potential, heterosis or hybrid vigor. Hybrid genetic potential, scientifically known as heterosis or hybrid vigor, is the central phenomenon explaining the superiority of F1 chickens. It refers to the ability of the offspring, F1 hybrids, to surpass the average performance of their two purebred parents in certain productive characteristics. It's not simply a sum of the parents' attributes, but a multiplier effect that results in exceptional productivity. This potential is the main objective of crossing programs in poultry farming. For example, if pure line A lays 200 eggs per year and pure line B lays 180, an F1 hybrid from their cross could lay up to 300 to 320 eggs, exceeding not only the average, 190, but even the better of its individual parents. This increase in performance is the direct result of the unique genetic combination that occurs in the first generation. The manifestation of this potential is seen in a variety of crucial productive traits. This includes a faster growth rate in broiler chickens, more abundant and persistent egg production in layers, better efficiency in converting feed into product, whether meat or eggs, and greater general resistance to diseases and environmental stress. The F1 bird is more robust and efficient than either of its pure parents. In essence, hybrid genetic potential is the magic of genetics applied to poultry farming. It's what allows the industry to produce meat and eggs so efficiently on a large scale. However, as we'll see, this magic is ephemeral in terms of inheritance, which makes it valuable as a final product but not as breeding material for the next generation. 7. Heterozygosity in F1 hybrids. Heterozygosity is the key genetic condition underlying the incredible performance of F1 hybrid chickens. An individual is heterozygous for a gene when it possesses two different alleles for that gene, one inherited from each parent, as opposed to homozygosity where both alleles are identical. F1 chickens are genetically diverse, carrying a wide variety of distinct alleles that come from their two parental pure lines. This high heterozygosity is fundamental because it allows for the expression of a wider set of beneficial genes. By having two different alleles for many traits, the probability that at least one of them will be the dominant and desirable allele significantly increases. This contributes to the genetic robustness of the hybrid, as they have more genetic options to adapt and perform optimally. Furthermore, heterozygosity plays a crucial role in masking the effects of less desirable or even harmful recessive alleles. If one of the parental pure lines carries an undesirable recessive allele, it's highly probable that the other pure line will contribute a functional or desirable dominant allele for the same gene. Since dominant alleles are expressed over recessive ones, the negative effect of the recessive allele is hidden or masked in the F1 hybrid chicken. In contrast to the homozygosity of purebreds, the heterozygosity of F1s is what gives them their burst of performance and vigor. It's the result of carefully selecting distinct pure lines that, when crossed, complement each other's genetics. This unique combination is what makes F1 hybrid chickens so valuable in commercial production, but it's also what limits their ability to be effective breeders. 8. Optimal expression of dominant genes. One of the pillars of high performance in F1 hybrid chickens is the optimal expression of dominant genes. Thanks to their heterozygous condition, where they possess different alleles from each parent for the same gene, the F1 has a high probability of inheriting at least one copy of the most favorable dominant alleles from each parental pure line. This means that the best genes from both sides are fully expressed. Consider a practical example. One pure line might have a dominant gene that confers an excellent growth rate, while the other pure line might have a different dominant gene that grants high resistance to a specific disease. In the F1 hybrid chicken, both dominant genes will be expressed simultaneously. This results in a bird that not only grows rapidly, but is also robust and resistant to that disease. This combination of dominant alleles is what gives the F1 its competitive advantage. There are no significant genetic compromises, as the desirable dominant traits from both lines are present in the offspring. It's a genetic synergy where the whole is greater than the sum of its parts. This optimal expression is the ultimate goal of planned crossing programs. Geneticists intentionally seek pure lines that, when crossed, maximize this manifestation of positive dominant alleles, resulting in an F1 individual that surpasses either of its parents in overall performance. However, this ideal configuration is difficult to maintain in subsequent generations, as we'll see, due to genetic recombination. 9. Masking of undesirable recessive genes. A crucial genetic benefit arising from the heterozygosity of F1 hybrid chickens is the masking of undesirable recessive genes. Purebreds, despite their uniformity and stability, can carry recessive alleles that, if expressed in double dose, i.e., in a homozygous recessive condition, could result in unfavorable or even harmful characteristics, such as genetic diseases, lower productivity, or structural weaknesses. When two different pure lines are crossed to produce the F1, it's highly probable that if one pure line contributes an undesirable recessive allele, the other pure line will contribute a healthy or desirable dominant allele for the same gene. Since dominant alleles are expressed over recessive ones, the negative effect of the recessive allele is hidden or masked in the F1 hybrid chicken. This confers greater robustness and viability to the F1. Although the parental pure lines may have certain hidden weaknesses in their genome, the combination in the F1 prevents these weaknesses from manifesting. For example, if a recessive gene causes a specific susceptibility to a disease, recessive, and the other pure line contributes the dominant allele for resistance, the resulting F1 will be resistant, despite still being a carrier of the susceptible allele. This masking mechanism contributes significantly to the overall vigor of hybrids. It minimizes the expression of negative characteristics, which translates into healthier, stronger birds with greater productive efficiency. It's part of the magic that makes the F1 so superior, but it's also one of the reasons why breeding F1s is counterproductive, as the risk of these recessive alleles being expressed in the F2 increases considerably. 10. Examples of genetic potential in F1. The genetic potential of F1 hybrid chickens manifests impressively in several key characteristics, which is why they dominate the global poultry industry. These concrete examples illustrate the superiority achieved by crossing carefully selected pure lines generating birds that far exceed their purebred ancestors in terms of commercial performance. One of the clearest examples is higher egg production. While a purebred hen might lay between 150 and 200 eggs per year, an elite F1 hybrid layer can easily exceed 300 to 320 eggs in its productive cycle, while also maintaining excellent shell quality and egg size. This volume is unattainable for most purebreds without the advantage of heterosis. Another outstanding example is seen in the rapid growth and feed efficiency of hybrid broiler chickens. An F1 broiler can reach a market weight of 4.5 to 5.5 pounds in just 35 to 45 days, with exceptional feed conversion, requiring less than 2 pounds of feed for every pound of weight gained. Purebred meat breeds would take much longer and consume significantly more feed to reach the same weight. Furthermore, F1 hybrids typically show greater general disease resistance and higher viability. They are more robust birds, better able to withstand the stress of intensive management, and less prone to certain common ailments. This strength contributes to lower mortality rates on farms, which directly translates to greater profitability for the producer. These examples demonstrate that the genetic potential of the F1 is not an abstract concept, but a measurable reality in poultry production. It is the culmination of precise genetic design, creating an animal optimized for efficiency in its productive life, but not as a reproductive link for subsequent generations. 11. Commercial purpose of F1 hybrids. The commercial purpose of F1 hybrid chickens is fundamental to understanding why they are not used for breeding. These birds are the final result of an extensive and costly genetic improvement program specifically designed for a single objective: to maximize the production of a final product, whether eggs or meat, in the most efficient and profitable way possible within a determined life cycle. They are not lines intended to perpetuate naturally or to be the basis for the next generation of breeders on a commercial farm. They are comparable to a high-performance racing car, built to win a specific race, but not to be mass-produced by a hobbyist in their garage or to be the basis of future vehicle models. Their genetics are fine-tuned to the maximum for the task for which they were created, not for reproductive stability. Genetic companies invest heavily in research and development to create these hybrid lines. Their business model is based on selling these F1 birds to producers in each production cycle. The poultry farmer, in turn, benefits from the predictability and high efficiency they offer, which translates into greater profitability in their operation. It is a relationship of interdependence where each party fulfills a specific role. Therefore, the idea of using F1 hybrid chickens as breeders on a commercial farm is contrary to their design and purpose. Attempting to breed them would not only fail to maintain their genetic potential, but would also result in lower performing offspring, which would negate the commercial advantages for which they were created in the first place. They are use and dispose birds in the genetic sense to optimize production. 12. Crossing commercial hybrids. F1, F1. Crossing hybrid chickens, F1, F1, is the scenario that creates confusion and leads to the loss of valuable genetic potential. When a producer, due to lack of knowledge or an attempt to save costs, decides to mate two chickens that are already first-generation hybrids with each other, they are creating what is known as a second filial generation, F2. At first glance, it might seem like a logical idea. If my F1 chickens are so productive, their offspring should be just as good, right? However, genetically, this is where the perfect recipe of the F1 begins to unravel. The F1, being highly heterozygous with many unique combinations of alleles, does not transmit its genetic combination in an orderly manner to the F2. This type of cross is not part of the genetic improvement program designed by specialized companies. In fact, it's precisely what they seek to avoid if the goal is to maintain commercial productivity. The results of an F1x-F1 cross are highly variable and unpredictable, which contrasts sharply with the uniformity and consistent performance of the original F1 birds. The F1-F1 cross is the direct cause of the dilution of genetic potential and the loss of productive efficiency in the offspring. It's the point where the planned breeding strategy deviates, leading to a generation of birds with very different and generally inferior characteristics compared to their high-performance hybrid parents. 13. Dissolution of genetic potential in F2. The dissolution of genetic potential in the second filial generation, F2, resulting from the cross between two F1 hybrid chickens, is the main reason for the drop in productivity. Unlike purebreds, which transmit their characteristics predictably, the complex genetic mosaic that gives the F1 its potential breaks down when they reproduce. It's like trying to copy a complex work of art by hand. The subtleties and perfection of the original are lost in the replica. The high performance of the F1 is based on a specific and optimal combination of heterozygous alleles. However, when F1 hybrids mate, their gametes, eggs and sperm, are formed through a process called segregation and recombination. This means that the alleles that were perfectly combined in the F1 father or mother separate and regroup in new ways in the F2 offspring, completely randomly. The result is that the F2 loses the uniformity and ideal gene combination that characterized the F1. While the F1 was genetically very similar to each other in terms of performance, the F2 will be a heterogeneous mix of individuals with different levels of productivity. Some might be decent, others poor, and rarely will any reach the level of their F1 parents. Therefore, the dissolution is not a total loss, but a genetic redistribution that dilutes the concentration of beneficial alleles and increases the probability of less favorable combinations. The genetic potential disperses, leaving a subsequent generation that is not commercially viable due to its inconsistent and generally inferior performance. 14. Segregation and genetic recombination in F2. Segregation and genetic recombination are fundamental biological processes that explain the dissolution of genetic potential in the F2. These mechanisms occur during the formation of gametes, eggs and sperm, in F1 individuals, and they are why F2 offspring are not faithful duplicates of their hybrid parents. During segregation, the two alleles for each gene that an F1 individual possesses, one from each original purebred parent, separate during gamete formation, so that each gamete receives only one of those two alleles. If an F1 has alleles A and A for a gene, 50% of its gametes will carry A and 50% will carry A. This already introduces variability. Recombination goes a step further. During meiosis, the process that forms gametes, segments of chromosomes can exchange between homologous chromosomes, the one from the mother and the one from the father. This creates new combinations of alleles on the same chromosome. While this is excellent for the long-term genetic diversity of a species, for an F1 hybrid designed for a specific combination, it disrupts that winning formula. When gametes from two F1 individuals, each with their own random combinations of alleles due to segregation and recombination, unite to form an F2 zygote, the result is a genetic lottery. The optimal combinations of alleles that conferred high genetic potential to the F1 are very unlikely to be recreated with the same precision and consistency in every F2 individual. Consequently, the F2 is not a uniform population of high-performing clones. Instead, it's a heterogeneous mixture of individuals with a wide range of genotypes and, therefore, phenotypes. It's this genetic shuffling of the deck that explains why the performance of F2 chickens is so variable and generally inferior to that of their F1 parent. 15. Loss of uniformity in F2. The loss of uniformity is one of the most noticeable and detrimental consequences of attempting to breed F1 hybrid chickens to obtain an F2 generation. While a flock of F1 chickens impresses with its homogeneity in size, development, plumage, and production, a flock of F2 chickens resulting from their cross will show marked heterogeneity that directly affects farm efficiency and profitability. Imagine a group of F1 layers, all start laying eggs more or less at the same time, their eggs are of consistent size and color, and their feed consumption is predictable. In contrast, a flock of F2 chickens would show wide variation. Some chickens might start laying late, others might never reach the desired egg size, and some might be significantly less productive or more susceptible to diseases than their flockmates. This lack of uniformity extends to almost all productive traits. In F2 broiler chickens, we would see large differences in growth rate, final weight, body conformation, and feed conversion. This makes flock management extremely difficult, as a standard feeding or management program cannot be applied to birds that are at such disparate stages of development or production. For a commercial producer, uniformity is money. It allows for optimizing feeding programs, space management, egg collections, or slaughter dates. The loss of uniformity in the F2 means that each bird almost requires individual management, which is unfeasible in large-scale operations. This is why the predictability of F1s is so valued, and the variability of F2s is so undesirable. 16. Increased expression of harmful recessive genes. One of the most negative and least visible effects of crossing F1 hybrid chickens is the increased likelihood of expression of harmful recessive genes in the F2 offspring. As we mentioned, the heterozygosity of the F1 is excellent for masking these undesirable alleles, as a healthy dominant allele usually covers the effect of the defective recessive allele. However, the genetic lottery of F1xF1 reproduction drastically changes this outlook. When two F1 hybrids, both carriers of the same harmful recessive alleles, though masked, are crossed, there is a 25% probability in each F2 offspring of inheriting two copies of that recessive allele. When this occurs, the recessive gene is expressed, as there is no dominant allele to mask it. These alleles can cause a variety of problems, from productive weaknesses to significant health issues. These recessive genes can manifest as lower viability, increased susceptibility to certain diseases, physical abnormalities like weak legs or plumage problems, or simply a marked decrease in individual productivity. For example, if a recessive gene causes a reduction in egg numbers or slow growth, these traits will appear in a significant portion of the F2 population. The emergence of these genetic defects and weaknesses is one of the fundamental reasons why the F2 is so inconsistent and less productive than the F1. Genetic companies invest enormously in selection programs to minimize the presence of these undesirable alleles in their pure lines, but in the F2, without the genetic control of the initial cross, these problems can resurface, compromising profitability and animal welfare. 17. Lower productive efficiency in F2. Lower productive efficiency is one of the most direct and detrimental consequences of attempting to obtain an F2 generation from F1 hybrid chickens. While the F1 is genetically optimized to convert feed into eggs or meat extremely efficiently, the F2 loses this advantage, which directly impacts the profitability of any poultry operation. In terms of egg production, F2 chickens generally lay fewer eggs than their F1 mothers, and often, these eggs may be smaller, have poorer shell quality, or their laying is more irregular and less persistent over time. This means that more F2 chickens are needed to produce the same number of eggs as a smaller number of F1s, increasing maintenance and feed costs per egg produced. For broiler chickens, efficiency decreases in feed conversion and growth rate. F2 chickens will take longer to reach the desired market weight and will consume significantly more feed to do so. This raises production costs per pound of meat, making the operation less competitive and profitable compared to using specialized F1 chicks. This lower efficiency translates into higher operating costs and lower income for the producer. The F2 not only performs less individually, but the variability within the flock, point 15, exacerbates the problem, making homogeneous feed management and production scheduling difficult. The economic optimization that characterizes F1 chickens simply disappears in the F2, making their commercial use unfeasible. 18. Unpredictability of performance in F2. One of the biggest disadvantages of breeding F1 hybrid chickens to obtain an F2 is the unpredictability of performance. Unlike F1 birds, which offer highly consistent and predictable results in terms of egg production, growth rate, and efficiency, F2 offspring are a true genetic lottery, where results vary wildly from one individual to another and from one batch to another. Commercial poultry farmers rely on predictability to plan their operations, calculate costs, project income, and manage their resources efficiently. If they buy F1 pullets, they know with a high degree of certainty how many eggs they will produce per hen in a given cycle, how fast they will grow, and how much feed they will need. This reliability is fundamental to the economic viability of the farm. However, with the F2, this predictability disappears. A flock of F2 chickens might include some birds with acceptable performance, but many others will be very poor. There's no way to know beforehand what percentage of the flock will be productive or when they will reach production targets. This makes effective management impossible, as uniform feeding, lighting, or health programs cannot be applied. Ultimately, the unpredictability of performance in the F2 represents a significant financial risk for any producer. It leads to inefficient management, wasted resources, and ultimately, an unprofitable operation. It is for this reason that the F2 has no place in commercial poultry farming, where efficiency and predictability are synonymous with success. 19. Role of genetic companies. Genetic companies play an irreplaceable and strategic role in modern poultry farming, and their role is key to understanding why hybrid chickens do not inherit their genetic potential. These companies don't just breed chickens. They are cutting-edge genetic research and development centers, investing millions in science, technology, and highly specialized personnel. Their most valuable assets are their pure genetic lines. These lines are the result of decades of intensive and rigorous selection, where animals with the best genes for characteristics such as fertility, hatchability, egg size, disease resistance, feed conversion, and body conformation are chosen. These pure lines are maintained in extremely high biosecurity facilities, and their genomes are closely guarded as trade secrets. The core business of these companies is the creation of F1 hybrids. Through complex crossbreeding programs, often 3- or 4-way crosses, not just direct to pure lines, they combine these secret pure lines to produce the high-performance commercial hybrids sold to poultry farmers. They are the only ones who have the complete recipe and the genetic ingredients to produce those F1 chickens with their exceptional potential. Therefore, the commercial producer is entirely dependent on these companies for their production birds. Attempting to breed F1 hybrids on the farm is to ignore the crucial role of these companies and the value of their genetic research. Genetic companies ensure that the poultry farmer always receives the highest quality F1 product with guaranteed genetic potential, thereby maintaining the efficiency and profitability of the industry on a global scale. 20. Recommendation for commercial producers. The key and fundamental recommendation for commercial poultry producers is simple and direct. To ensure maximum productivity, profitability, and predictability in your operation, you should always purchase day-old F1 chicks directly from specialized genetic companies. Attempting to breed from F1 hybrid chickens already on the farm is a counterproductive practice that will result in financial losses and frustration. F1 hybrid chickens are a finished product designed for a specific purpose, to efficiently produce eggs or meat during a life cycle. Their exceptional genetic potential is fully manifested in that first generation, but it is not consistently transmitted to the offspring. Investing in the correct first link of the productive chain is the smartest and most economically viable decision for any serious poultry farmer. By purchasing directly from recognized genetic houses, producers benefit from decades of research, selection, and rigorous quality control. They receive birds with a proven performance history, guaranteed health, and the uniformity necessary for efficient farm management. This eliminates uncertainty and maximizes the chances of success in a competitive market. It's not that hybrid chickens are bad breeders, it's that they were not designed for that purpose. They are the final result of a complex genetic process that culminates in their high productive efficiency. The smartest strategy for the poultry farmer is to fully leverage that potential by acquiring the appropriate F1 product for each cycle, instead of trying to recreate the complex and secretive genetic art of specialized companies. And there you have it, folks. If you're someone who dreams of food independence, with fresh eggs from happy chickens you raised with your own hands, then this content is your first step. We've broken down every detail so that, no matter your prior experience, you can start producing your own laying hens at home. Imagine the satisfaction of collecting your own eggs every morning, knowing exactly where they came from and how they were raised. Don't just learn the theory, take action now, but information alone won't get the job done. It's time to roll up your sleeves and make your mini home farm a reality. So you don't miss a single tip, trick, or update on how to achieve it, make sure to subscribe to our channel right now. Don't forget to hit that notification bell so you're the first to know about our new videos, and of course give us a thumbs up if this content was helpful to you. Your support helps us continue sharing valuable knowledge with our community. Plus, share this video on your social media so more breeders can learn from this important information. To your success, fellow breeder. Until next time.